So today we are covering chapter 9 and have already scrolled here to answers. PDF was posted on Canvas, so you could have gone through it if you had the time. But answers are here, and of course question is repeated, so you'll be able to see the entire question. So first one, provide UPAC name of the major product of a reaction of 1-ethyl cyclopentene with hydrogen bromide. That's typical electrophilic addition to an alkene, and addition follows Markovnikov rule. Reaction proceeds through carbocation as the reaction intermediate. So we have here 1-ethyl cyclopentene on the left as reactant, and you can see it has trisubstitute and disubstitute carbon. So more substitute and less substitute carbons. So hydrogen of hydrogen bromide will add to less substitute carbon because that gives intermediate more substitute carbocation. And then bromide anion as a nucleophile reacts with carbocation, forms a bond to carbocation electrophile to give the final product. And then you need to name it. So name of this product is 1-bromo 1-ethyl cyclopentane. So from 1-ethyl cyclopentene with hydrogen bromide we obtain 1-bromo 1-ethyl cyclopentane. Question number 2. Which of the following undergoes a reaction with proton or a proton donor? So proton or proton donor, proton is an electrophile, proton donor is source of an electrophile. So question is really which of the following is a nucleophile? And you should answer that question by eliminating wrong answers. First one, A is a free radical. If you recall from chapter 6, free radical is actually an electrophile. Free radicals don't react with electrophiles. Sorry, free radical is electrophile, and they don't react with other electrophiles. They would react with nucleophiles such as double bonds. And that's what we have under B. We have double bond. You may recall from a previous meeting that pi bond can be donated, so that electron pair of pi bond can be donated. So that's actually a nucleophile. In other words, pi bond can be protonated. So B appears to be correct answer. Just to make sure, we should check C and D. So C is carbocation. Of course, proton is positively charged. Two positively charged species will not react with each other. They repel each other. Identical charges repel each other. Also, carbocation is an electrophile, just like proton. Two electrophiles don't react with each other. And finally, the last one is bromoethane. That one actually does contain electrophile, this carbon attached to bromine, and you will learn more about it in chapter 12. But still, right now, you can certainly see that it is not a nucleophile. It cannot be protonated. There are free electron pairs from bromine, but bromine does not undergo protonation. So correct answer is B, 2B. Okay, so before I move on to next question, I'm going to check if there are any questions from the class. I don't see any. As usual, if you have questions, you can type them up in the chat, or you can unmute yourself and ask a question. Question number 3. A compound with molecular formula C10H13Cl reacts with 2 equivalents of bromine in the dark. How many rings does it have? So first, a reaction is with 2 equivalents of bromine in the dark. You may recall from chapter 7 that alkanes, saturated compounds, react with bromine and reaction is free radical substitution. But that requires presence of heat or light, typically light, because if you expose reaction mixture to ordinary ambient light, that's enough. So it's much easier to simply expose reaction mixture to the light than have to heat it. So that's the difference. So if reaction is carried out in the light, then you can expect free radical substitution. But if it's carried out in the dark, then the only possible mode of reaction is addition of bromine across a pi bond, in this case a double bond. And so reaction with 2 equivalents of bromine tells us that there are 2 pi bonds, because reaction is in the dark. So 2 pi bonds, so there are at least 2 unsaturations, and those are 2 pi bonds. Now, how many rings does it have? Well, if there are any unsaturations other than 2 due to double bonds or due to pi bonds, then those are going to be rings. And so we have to calculate degree of unsaturation. That's 2 times n plus 2 minus m. N is number of carbon atoms, 10. M is sum of the number of hydrogens and halogen atoms. That's 13 plus 1, 14. So 2 times 10 plus 2, that's 22, minus 14, that's 8. 8 divided by 2, there are 4 unsaturations. We know that 2 are pi bonds, so remaining 2 unsaturations are rings. And so correct answer would be 2 rings. So hopefully you know how to do calculation of degree of unsaturation. And again, don't forget halogens. This is overlapping chapter 8 and 9. In chapter 8, you learned how to do calculation of degree of unsaturation. And then in chapter 9, we covered specific reactions that identify pi bonds as unsaturations. And those reactions are typically addition of bromine or catalytic hydrogenation. Question number 4. What is the product of the following reaction? And so we have here chlorine in dichloromethane. Dichloromethane is the solvent. So chlorine, that's addition of chlorine across a double bond. Electrophilic addition of halogens across double bond, chlorine and bromine, is anti. That means that 2 atoms of halogen, in this case 2 atoms of chlorine, add anti on the opposite sides of double bond. They add from the opposite sides of the double bond. Mode of addition could be syn from the same side of double bond, so from the top or the bottom. So both reactants come from the bottom or the top, or anti, one from the top, one from the bottom. In cyclic compounds, cycloalkenes, anti-addition gives trans product, and syn addition gives cis product. So don't confuse cis trans with syn anti. Syn anti is mode of addition, and so if you're asked about mode of addition, those are correct terms, syn and anti. Cis and trans apply to products. So in this case, it's going to be anti-addition, but anti-addition gives trans product. So it's going to be trans dichloro compound. And so when we consider answers, A actually is not addition. There are 2 chlorines that replace these hydrogens. That's actually not a reasonable reaction. So that's not a reasonable reaction product. B is cis product, and that's actually a result of syn addition. So if reaction mechanism were syn, then this would have been correct product. But it's not syn, it's anti. C, that's actually allylic. Actually, it's not even allylic. This is allylic carbon, it's quaternary. So it's just a free radical substitution. It does not occur under these conditions, so that's not correct. And finally, D, we have trans, 2 bromines trans to each other, 2 chlorines trans to each other. That means that was result of anti-addition. And so D is correct product. Because it's trans, that means addition must have been anti. So pay attention. See, question 1 was regioselectivity. Regioselectivity means at which carbon atom, each of the reagent atoms ends up. That's regioselectivity. And stereoselectivity is things like this, where the product is cis or trans, where the mode of addition is syn or anti. Let me check if there are any questions. Because next is a little bit, how do you know it is syn addition? Well, that's covered in the chapter. Actually, it's not syn addition, it's anti-addition, but that's covered in the chapter, and you know that from the mechanism. So depending on the reaction mechanism. So you have to examine reaction mechanism. It's explained in the videos on YouTube that I posted on YouTube. Both those where I have some animations, and that one, chapter 9, where I followed the textbook and explained chapter 9 going through the textbook. So each mechanism involves particular mode of addition, syn or anti. Some actually would give a mixture, but that's less common. So what is stability of the following? Actually, it should be radicals, because when I wrote this question, I was going to put radicals or carbocations, and in this case, it's radicals. So we have free radical A, B, and C. So on the test, you will type up A, B, C, of course. And so you need to arrange them in the order of increasing stability from the least stable to the most stable. Stability of both free radicals and carbocations follows the same order for different reasons. And it's the least substituted is the least stable. So methyl is the least stable, and then primary, secondary, and tertiary is the most stable. In case of carbocations, this is the order of stability for electronic reasons, due to stabilization of the carbocation through hyperconjugation. So electron donation through hyperconjugation. In case of free radicals, reason is steric, because free radical is sp2 hybridized, and there is release of steric hindrance going from tetrahedral starting material to trigonal planar free radical. So, while reasons are different, the order is the same. Methyl, primary, secondary, tertiary. And of course, if you have three, then one of those four will be missing, but still you follow this order. And so if you identify them, A is actually secondary, is secondary radical. Carbon, that is the free radical, is bonded to two other carbon atoms. B is primary. This carbon, free radical carbon, is bonded to only one other carbon. And C is tertiary, because this free radical carbon is bonded to three other carbons. So order of stabilities is going to be B, primary, then A, secondary, and C, tertiary. You can see that methyl is not represented here. So BAC, and you would simply type it like this on the test. Next question is also about stability, but now about alkenes. So what is the stability of alkenes? And stability of alkenes depends on the two factors. Degree of substitution of double bond, just like free radicals and carbocations. And actually, when it comes to degree of substitution, the reason is the same as that of carbocations. It's stabilization, electron delocalization, stabilization, or in this case of double bond, through hyperconjugation. So this is a form of electron delocalization. So reasons are electronic. And that's the most important reason. So that's the first thing you're looking for. What is degree of substitution of the double bond? In a double bond, two carbons are bonded to each other with a double bond, and each carbon has two substituents. So in total, double bond has four substituents. In practice, it may have none if all four are hydrogens. That would be ethene, and that's the least stable alkene. And then the more substituents there are, the more stable it is. So one substituent, more stable than ethene. Two, more stable than one. Three, more stable than two. And four substituents is the most stable compound. Only if number of substituents is the same, then you look at configuration. Is it cis or trans? Trans is more stable than cis because there is greater steric hindrance in cis. And so we'll now look at this. And here we also have, we will see another complicating factor, and I will explain that in a minute. Actually, there's not much to explain, you'll just need to memorize it. So let's consider these four. So first thing that we are considering, and in this case it's going to be the only thing, is degree of substitution. So A is tetrasubstituted, so we expect it to be the most stable. B and C are actually both disubstituted. One must be more stable than the other, so we'll be looking at that. And D is trisubstituted. So the order of stabilities will be disubstituted, trisubstituted more stable, and A, tetrasubstituted, the most stable. So it's going to be one of those, B or C, then D and A in the order of increasing stability. Now, let's consider B and C. Difference between B and C is that in isomer B, we have both substituents on one carbon of the double bond. While in C, those two substituents are on different carbon. One carbon has each. Electron delocalization through hyperconjugation is more efficient in C when there is one substituent on each carbon. So for that reason, C is more stable than B. So you need to memorize that. that when there are two substituents on the double bond, then if those substituents are on different carbon, that's more stable than if they were on one carbon. So stability is B, C, D, A. Notice that C is trans. If there was cis isomer, it would have been more stable than cis. This one is cis isomer. A is cis isomer. So there is something more stable than that, and it will be trans, where methyl and ethyl, for example, are flipped. It will be trans isomer. But with these four that you have on the test, you would simply answer B, C, D, A. Okay, so let's see if there are any questions. Okay, no questions, so let's move on. Question number 7. Provide UPAC name of the product of hydroboration oxidation of 3,3-dimethyl 1-pentene. So the overall process is addition of water across a double bond, and less substitute alcohol is obtained. Actually, maybe I should also provide mechanism, or actually each step individually. So let me just do it quickly. So the mechanism of addition of borane is that boron adds to less substitute carbon of the double bond, and hydrogen adds to more substitute. The reason for this is in the energy of transition state, and that's again explained in the videos and textbook PDF. And then hydrogen peroxide oxidation results in conversion of borane group to hydroxyl group. So net overall result is addition of water across double bond, where hydroxyl group ends up on less substituted carbon. So this is regioselectivity question. Do you know at which carbon hydroxyl group ends up? And so if you did everything correctly, this is the product, and you need to name it. So this is pentanol, specifically 1-pentanol, and on carbon 3 we have 2 methyl groups. So product is 3,3-dimethyl 1-pentanol. Next question, number 8. Which reagent would accomplish the following transformation? And so here, if you compare product with the starting material, you can see that double bond has been cleaved, and it's replaced by two CH2OH groups. This is CH2OH, CH2OH. So these two carbons that carry hydroxyl groups have been connected by a double bond. Reagent that you know of that cleaves double bond. There is difference between double bond cleavage and addition to double bond. Addition to a double bond means that pi bond undergoes reaction, but carbon-carbon sigma bond is unaffected. So bond between two carbons remains, but it's no longer double, it's single, and something has added across the former pi bond. Cleavage means that bond is broken, so bond is cut between two carbons, and those two carbons are separated. And the reagent that does that is ozone. So reaction is ozonization. And then what are the final products depends on the workup. Workup could be oxidative workup with hydrogen peroxide, and then these two carbons would end up as carboxylic acids. And there are different types of reductive workup. Mild reductive workup with zinc in acetic acid or dimethyl sulfide results in aldehydes as reaction products. More vigorous reagent, more vigorous reductive workup involves sodium borohydride. That's a stronger reducing agent. And so that one reduces the intermediate all the way to alcohols. And so that means that reagent was ozone and workup was carried out with sodium borohydride. On the test, you would need to provide the reagent, and so you would write it like this. I'm not going to insist on the solvent, but solvent is dichloromethane, and hopefully you would know that. So that will be first step. Don't forget 1 and 2. You have to indicate 1 and 2 for the first and second step. If you don't indicate 1 and 2, that means we are mixing everything together, and the reaction wouldn't work like that under those conditions. So this is the way you would write it on the test. So without superscripts, subscripts, anything like that. Okay. Question number 9. Which of the following carbocations is likely to undergo rearrangement? So rearrangement of carbocations is intramolecular reaction and involves conversion or rearrangement of less stable carbocation into more stable. As you know, order of stabilities of carbocations is primary, secondary, tertiary. Primary are rather unstable, so they're unlikely to be reaction intermediates. So the most common case that you will encounter is rearrangement of less stable secondary carbocation into tertiary. Tertiary are unlikely to rearrange because they're already stable. So what you're looking for is secondary carbocation that has possibility for rearranging into a tertiary by shift of a hydrogen or methyl group or alkyl group. So you're looking for secondary carbocation that next to it has a hydrogen or methyl, so that when it shifts, it's going to give tertiary carbocation. And actually, A is carbocation like that. It's secondary. This carbocation, this carbon, is connected to 2 other carbons, so that's secondary. And if either of these 2 methyl groups shifts, that actually gives C. That's why I provide A as C. So you see, if either of these 2 methyl groups shifts to the carbocationic carbon, now that's new carbon-carbon bond. And carbon that this methyl group left is now carbocation. So you see, we went from secondary to tertiary. So A is correct answer. You should check the rest just to make sure that you didn't make a mistake. So B, this is secondary carbocation, but there is nothing in the neighborhood that can shift to give more stable carbocation. Here is oxygen atom, and you can't really shift anything to give. And also oxygen doesn't tolerate positive charge very well, because when there is a shift, that means from the neighboring atom, some group is going to leave to form bond with carbocationic carbon. And so that carbon, that group has left. Now that carbon is going to acquire positive charge and be cation. And oxygen is not very good cation. It's highly electronegative, doesn't tolerate electron deficiency very well. C, it's already tertiary. So yes, we could, for example, shift this hydrogen to this carbon, and then we would have tertiary carbocation here, but there is nothing to be gained by that. There is no energy gain, because we go from one tertiary to another tertiary, and that's not really efficient. And here we have another secondary carbocation, but any shift of any of these hydrogens, these are CH2 groups, just gives another secondary carbocation. So just like previously under C, where rearrangement would go from one tertiary to another tertiary, and there is nothing to be gained by that. Here, rearrangement would go from one secondary to another secondary carbocation. Again, nothing to be gained by that. Rearrangement will occur only if carbocation is converted to more stable carbocation, secondary to tertiary. So also C and D are not correct answers. So correct answer is A. And finally, question number 10, what was the starting material? So on the tests, you can see there are 3 components to reaction: starting material, or substrate, reagent, and product. And typically you are given 2 to figure out third. Most commonly you are given substrate, reagent, and what is the product. But you could be given substrate and product, what was the reagent, and that was question earlier, question 8. We were given substrate, product, what was the reagent. Or, as in this case, we were given reagent and product, what was the starting material. So Reaction is permanganate with heat. So permanganate with heat actually cleaves double bonds. That's the second reagent, other than ozone, that also cleaves double bonds. Permanganate at low temperature adds two hydroxyl groups. That's hydroxylation reaction. So if this was ice bath instead of heat, if this said ice bath or like 0 degrees Celsius or 5 degrees Celsius, 0 degrees Celsius is temperature of ice bath. Sometimes we write 5 degrees Celsius because 0 is ice bath outside the flask. In the flask, temperature is frequently a little bit higher, and if you measure it, it would be like 3 degrees, 5 degrees, something like that. So, because reaction is a little bit exothermic, and then you can never really get that 0. So, in any case, this is heat. This is not ice bath. With heat, that means that we are cleaving double bond, and products with permanganate are always carboxylic acids. So when you work this backwards, what was the starting material? If permanganate cleaves double bond in such a way that each carbon of the double bond ends up as carboxyl group, that means those two carboxyl groups must have been connected by a double bond. And you simply connect them with double bonds. So you count how many carbons are here. 1, 2, 3, 4, 5, 6, 7. That means 7-membered ring with a double bond. And if you label this as carbon 1, then on carbon 2 you have methyl group. So this is that old carbon 1, carbon 2 is methyl group. Just keep in mind the nomenclature. If this is carbon 1, then other carbon of double bond for nomenclature purposes. This is just to identify where methyl group is. For nomenclature purposes, if this is carbon 1, this has to be carbon 2. And actually, that's not good naming because 1, 2, then this would be 7. This 7-methyl cycloheptene. So this bottom carbon of the double bond has to be carbon 1, this is carbon 2, and this is carbon 3. So starting material was 3-methyl cycloheptene. Okay, so this completes review of chapter 9. I'm going to stop recording now, and then I will answer any questions you may have.